I'm going to give you two reasons why they're really important. The first is with impedance matching. So let's say you've got your MP3 player, like your phone, and you measure that it gives 1 volt of output signal. It's sinusoidally varying, right? It's not always 1 volt. It pops up and down between -1 and 1 volt, but that's called a line voltage, and it's about 1 volt. And you select a speaker, and when you power the speaker from a good 1 volt source, it makes a nice sound. So you say problem solve, you connect your speaker to your MP3 player, and you discover it doesn't work. So you already know why, right? Why doesn't it work? The MP3 player puts out about ±1 volt. The speaker works great on ±1 volt. You put them together, you get nothing. What's going on?
Well, is that MP3 player have like a Thevenin?
Right.
Implied Thevenin resistance, so it's not actually putting out.
So let's look at what that Thevenin resistance is, and let's, just to make the numbers easy, let's say it's equal to 990 ohms, and let's say our speaker is about 10 ohms, 10%, Lordy. And by the way, those numbers are fairly reasonable numbers. So my question is, this is now you've put in the Thevenin equivalent, and now let's find out how much power ever gets to those speakers. So in order to figure that out, it's going to be the voltage to the speakers times the current to the speakers. So what's the voltage to the speakers?
I can't see. Okay, now I can. Sorry, what did you say?
My question is let's just be a little bit, it's VS, but that's at the source. That's not at what the speakers see.
Right. So speaker to be at that 10 ohm resistor. So VS times V. Okay, so V at the 10 ohm equals VS times 10 over 10 plus 20.
10 plus
990, I mean, yeah, that's right.
Which is big. All right. So that's our V speaker. And then we need to multiply by our I speaker, which is
voltage over the, so current divider, I speaker equals,
is it a current divider? Is current being divided through two different areas?
No, it's just be through those added together. So
Just
over
added together.
1,000.
Over 1,000. All right. So we've got something that looks like 10 VS over 1,000,000 or VS over 100,000. So squared. So yikes, that's not really great. If our VS was 1 RMS, 1 volt RMS, we've got 1 over 10,000. We've got 100,000th of a watt being delivered to our speaker. So it's not surprising that we didn't hear very much. Okay, so this is our first design. And that's obviously not going to work. So let's do another design. Second design is we're going to take that same MP3 player, and up until this lecture, before this lecture, how would you have handled fixing that problem?
Would increase that voltage.
You can't increase the voltage. It's your phone.
Okay, then I would try to decrease that resistance.
This resistance, this is built into your phone. You can't change it.
Okay, then I'm not really sure.
Well, how could you? You've seen these buffer circuits before, right?
Oh, right. Yep.
So you could design this. And now just quickly, let's do the same thing to the speaker. It's V speaker and it's I speaker. So now, what's the voltage that gets to the speaker?
Voltage that gets the speaker.
How much? Yeah. How much? What's the voltage across here?
V out.
This is V speaker. Right. Now it's just simply VS. Because there's no current, that current can't flow into an op amp. So this 990 ohm resistor drops nothing. And so the Thevenin equivalent to the left of this, to the left of the output of the buffer, looks just like a pure voltage source. That's the benefit of the buffer. It just removes the Thevenin equivalent impedance entirely.
Okay, that makes more sense.
And now, what's the current going through the speaker?
VS over 10 ohms.
Yeah. So now we've got VS squared over 10. Compare that with this number. That's 10,000 times better, right? That's much better. Except now you've got an op amp. And what's not shown to the op amp is that it's got to be powered. And that means you've got to have batteries. And adding an extra battery powered thing that you've got to keep charged and keep track of it's physically large to have batteries, and you've always got to be worried about keeping them charged. So that's not an ideal design. If you were making this, you would probably be willing to give up some of your amplification in order to make it perfectly passive. So you'd never have to worry about charge. You could take it on any kind of trip. You could just pull it out of your backpack after not being used for a year, and it would just work. So the way to do that is putting in a transformer. Because I'm going to slightly change this. I think you'll be okay if I change it from 990 ohms to 1,000 ohms. It's almost the same. It makes the numbers work out so much more easily, better. And if anything, that makes the problem even harder to solve, right? Because it's more Thevenin impedance. So what does the load have to be in order to have the most effective power transferred to it? What does this whole piece over here have to look like for maximum power transfer?
Would it be that Thevenin equivalent of 10 over the N factor squared?
Oh, you're already jumping to the solution. What I'm asking, even a simpler question. I'm saying, if you could design your load to be anything you wanted, what would that load be to dissipate the most power? If that load was 0, how much power would it dissipate?
None.
None, because there's no voltage across it. If that load was infinite, how much power would it dissipate?
All of it.
Well, all of it, but if it was infinite, how much would that all of it be?
Okay, so
remember, the power across your load is equal to the current through the load times the voltage across the load. When we made that resistor 0, we said, well, now it's got no voltage across it, so the power dissipated will be 0. When we make this resistor infinite, how much power will there be? Think about this equation. Yes, all the voltage will be there, but what will happen to the current if we make it infinite? If we make the resistance infinite?
0, no current.
0. And so now there's no current, and so once again, there's no power dissipated. So if we make this resistance 0, it's bad. If we make it infinite, it's bad. There's got to be something in between there where it's optimal. Do you remember what it is? You worked it out in circuits 1, and we talked about it in circuits 2 briefly.
1 mega ohm.
No, it's equal to it's when RL, in general, if this was a Z, when your load impedance is equal to the complex conjugate of your source impedance, that's where you've got the greatest power transfer. And in circuits 1, you talked about it without the complex conjugate. You just said when the load resistance is equal to the source resistance, you get maximum power transfer. And since this is a purely real number, it happens when your Z load equals 1,000. Make sense? This is just something that you have to memorize. You can work it out. You can write the equation for what is the power dissipated by this load as a function of its resistance. And then you can take its derivative with respect to resistance, set that derivative equal to 0, and you'll find out that it has a maximum when ZL is equal to the complex conjugate of your source resistance. So that's the maximum. So the maximum power transfer theorem. I think you might have not been in class for that one. It says that if you've got a source and you've got a equivalent, Thevenin equivalent impedance of that source, which you can't change. You can't change the source impedance. You can't change the voltage source. And you want to know what load will dissipate the most power. It's equal to the complex conjugate of the source. So that's just another thing to know. And so given that information, we may be able to use a transformer to get you there. All we need to do is to say, using this equation down here, that our original impedance over our n squared, or original, equals our desired source impedance. So our original is 10 divided by n squared, has to equal our desired impedance, which is 1,000. And so if you cross multiply, we get 10 equals 1,000 n squared, which means n squared is equal to 100, which means n, is that right? Which means n squared is equal to 1 over 100, which means n is equal to 1 over 10. And so now we've got now you can design the circuit. Have a lot of things over here, just has a couple on this side. And by the way, I'm drawing them with different numbers of loops to sort of show you what that n is. But the usual schematic just has the same number of loops on both regardless. And then that's our answer. And by designing this device, we'll have more power transfer than our naive device without an op-amp, less than our op-amp, but it will not require any external source. So as an example for this one, we might have N1 with 1,000 loops and N2 with just 100 loops. And that would work as a design. And I'm not going to go through the whole thing to find out what the power of the speaker is, but you'd find it just the same as we did it so far before. You'd replace this with its Thevenin equivalent, which now looks like this. Oh, maybe I will do it. And so now the current through the speaker would be equal to Vs over 2,000, because it looks like two 1,000 ohm resistors. That's the current. The voltage is just half. And so now you've got Vs squared over 4,000 watts. So way better than Vs squared over 100,000. Not as good as Vs squared over 10, but it may be good enough for your applications that you still hear something and you don't have to worry about the batteries.